A system of linear equations is just two or more equations considered together, involving the same variables. You're looking for the values of the variables that satisfy all equations at once. The most common case is two equations in two variables, where the solution is the point of intersection. Geometrically, each equation represents a line. So solving the system means finding out where those lines cross, if they cross at all. Think of it like two jet airplanes flying through a two-dimensional sky. If their paths intersect, we've found a solution. If they never meet, they're flying parallel forever, like soulmates who never get to do it. That's a system with no solution. And if they're on top of each other the entire time, that would be a violation of all norms, including those of the Federal Aviation Administration. The graphical method involves plotting each equation on the coordinate plane and visually identifying the point where the lines intersect. That intersection point is the solution to the system, the values of x and y that satisfy both equations simultaneously. This method gives a nice geometric interpretation of the problem. However, it's not always precise, unless your graphing skills are flawless and your ruler isn't slightly bent. Also, good luck if the coordinates are fractions. In that case, even with impeccable graphing skills and a laser-straight ruler, your headache is guaranteed. Substitution is a powerful technique for solving a system when one of the equations is already solved for a variable, or can be easily manipulated to do so. You start by isolating a variable in one equation, then substitute that expression into the other equation. This removes one variable and allows you to solve a single variable equation. After that, you back-substitute to find the other value. It's an efficient method, especially when the substitution is clean and fraction-free. Think of it like detective work. One equation gives you a lead. Say, y is equal 3x minus 2. You use that info to arrest the first suspect. Once you catch the first one, let's say x, you interrogate them, and under pressure, they reveal y's hiding place. As far as I am concerned, you can even waterboard x. You will receive full mark for capturing the right values, regardless of your methods. Elimination is about getting rid of one variable by combining the two equations. The goal is to manipulate the equations, often by multiplying one or both, so that adding or subtracting them causes one variable to cancel out. Once one variable is gone, you're left with a simple equation in the other variable, which you can solve directly. You then substitute that result back into one of the original equations to find the remaining variable. This method is especially efficient when the coefficients are already set up nicely for cancellation, or can be aligned with minimal effort. Think of these two equations as two waves containing all the information about x and y. But there's a lot of noise, and it's hard to see the answers clearly. Elimination is a noise-canceling technique. You generate an equal and opposite force by scaling the equations, so that one variable cancels out entirely. What remains is a much simpler signal, an equation in one variable that's finally clear and easy to solve. It's algebra for audiophiles. Eliminate the static, find the melody. When solving a system using elimination, you may encounter three outcomes, each with its own algebraic fingerprint. If the lines intersect at one point, you'll get a unique solution, just like normal. If the lines are parallel, elimination leads to a contradiction, like 0 is equal to 5. This tells you there's no solution, The lines never meet. If the lines are identical, elimination wipes everything out and gives 0 is equal to 0. This means every point on the line is a solution, infinitely many solutions. So how do you tell the difference? Pay attention to what's left after elimination, either a valid equation, a contradiction, or an identity. This is one of those word problems where you wonder, why are these adults bringing so many kids to a $10 concert? Is it a children's choir? A heavy metal rock band? A Taylor Swift cover act where kids get in cheaper? Whatever the backstory, the math is the same. One equation tracks the number of people, the other tracks the money. And solving the system reveals how many stressed parents and hyper kids are in the audience. This one is also rather weird. Why don't you just ask the plumber directly how much he charges? But no, we've decided to reverse engineer his business model using 2 job invoices. Maybe you are a nosy neighbor who found these 2 invoices in the recycle bin and you have nothing else to do with your life. In the golden age of Babylon, long before calculators and capitalism, citizens paid their taxes the traditional way, in goats and barley. It was the law. You either paid 3 goats and 10 sacks of barley, or 4 goats and 5 sacks of barley, your choice. No one questioned it. Everyone just paid and got a polite nod from the tax collector and maybe a goat horn on the way out. But then came a progressive king, King Hammurabi, who introduced the shekel to modernize the economy. He proclaimed, "Henceforth, taxes shall be paid as a flat 100 shekels per citizen." Goats and barley are so 18th century BCE. That's when chaos erupted. Citizens asked, "How many shekels is a goat worth? How much for a sack of barley?" Bartering became awkward. Fights broke out at the market. Goats were dramatically overvalued. Barley merchants started promoting veganism. Desperate, the citizens turned to the kingdom's highly respected mystic and math guru, Qalmu-Sin the Sapient. He listened. He scratched 2 linear equations on a clay tablet. 3x plus 10y equals 100 and 4x plus 5y equals 100. Where x is the value of a goat in shekels, and y is the value of a sack of barley. He solved the system mentally like a wizard, stood before the crowd, and declared, "A goat is worth 20 shekels and a sack of barley is worth 4 shekels. Now stop yelling." Markets stabilized. Farmers rejoiced. King Hammurabi nodded smugly. And thus, from tax fairness, bartering disputes, and an inconvenient currency reform, the system of linear equations was born, not to pass exams, but to price goats.